Okay, hello students. So in today's class we'll learn about the concept of duality in linear programming problem. Okay. So for every linear programming problem there is an associated linear programming problem that is also known as the dual linear, or we call it dual LPP, dual linear programming problem. Okay, so given LPP is known as primal LPP, okay, and we create one LPP by doing some row and column transformation is called dual. Okay, so there are certain advantages of this dual linear programming problem. Okay, so one of the advantages, if primal contains a large number of decision variables compared to the constraints, then dual LPP reduce the number of transformation, number of iteration. Okay, so this is one of the advantages, and the second advantage is that this gives additional information as to how the optimal solution changes the result of the change in the coefficient. Change in the coefficients. Okay, because till now we were trying to minimize the cost of the objective function. Okay, cost or maximize the profit of objective functions. Okay, but this, with the help of this dual LPP, we will get to know if we add one more resource, okay, one additional resource, then how much the profit is going to be increased. Okay, if we reduce one resource, how much efficient are going to be the cost. Okay, so that information we can get it by analyzing dual LPP. Okay, and correspond to every linear programming problem we can construct the corresponding dual LPP by using some row and column transformation. Okay, actually we have to take the transposition of coefficient matrix, and with the help of that we can construct the dual LPP. So whenever you want to analyze such situations, like suppose you are working in a company and you want to check whether by adding one employee can we increase the profit or not. Okay, or by adding one employee into the team, how much profit is going to be increased. Then information you can get it by analyzing dual LPP. Okay, so let us understand what is it and how to convert a primal LPP into its dual form. Okay, so first of all, example, if you want to construct dual from primal, okay, what you need to do, first of all, convert given LPP, the primal, into its canonical form. Okay, so if you want to construct the dual from the primal, first of all, whatever LPP is given to you, you have to convert that into its canonical form. Then only you can convert it into its dual. So let me take one example. So the canonical form, general canonical form of an LPP can be written as maximize z equals to c1 x1 plus c2 x2 dot cn xn subject to the constraints. Okay, and the constraints are going to be a11 x1 plus a12 x2 plus dot a1n xn less than equals to v1 and a21 x1 plus a22 x2 dot a2n xn less than equals to b2, and the last constraints can be written as a m1 x1 plus a m2 x2 plus dot plus a mn xn less than equals to bn. Okay, so this LPP contains a small n number of variables and a small m number of constraints, and at last don't forget to put the non-negativity constraints. So x1 comma x2 comma xn all are greater than equals to 0. Okay, so this is the canonical form of the LPP. So you know, in the canonical form all the constraints are going to be the less than equality constraints. If not, then convert it into the less than equality constraints. Okay, now come to the dual of its primal. Okay, so for dual we're going to define a decision variable in the dual LPP. We're going to define decision variable correspond to each constraints. Okay, so one variable is going to be defined correspond to this one. Let us say this is y1. One variable correspond to this y2, and the last variable is going to be defined correspond to the last one. Okay, so number of constraints in primal is equals to the number of decision variables in its dual. Okay, and correspond to each primal variable we're gonna have one constraints in its dual. Okay, so let us do it. So dual. So if primal is maximization, then dual is going to be minimize. Minimize z prime equals to, okay. And now instead of this cost, these decision variables, dual decision variables, are going to be multiplied by resources, and we have to take the sum and then minimize it, okay. So the objective of dual is going to be b1 by 1 plus b2 by 2 plus dot dot bm ym, subject to the constraints, okay. And correspond to each column, we are going to have the corresponding constraint in the dual, okay. So correspond to the every column of the coefficient matrix in the primal, we are going to have the dual, okay. So dual constraints, so it is going to be a11, and now instead of primal decision variables, we'll take dual decision variables. So a11 y1 plus next one is going to be a22 sorry a21 y2 plus a31 y3 plus dot dot a m1 ym. Now since the primal contains the less than equality, so the dual will have the greater than equality, okay. And here instead of resource, the cost will come. So the next constraint is going to be a12 y1 a22 y2 a32 by 3 a m2 by m greater than equals to c2, okay. And similarly the last constraints is going to be a1n y1 a2n by 2 a3n yn by 3 plus dot dot a mn y m greater than equals to c, okay. And last, the non-negativity constraints, y1 greater than equals to 0, y2 by 3 dot dot y, all are going to be greater than equals to 0. So this is the corresponding dual, okay. Now understand this, how can we convert a given LPP into its dual by taking some examples. Okay, and before that I want to make a table that is going to help you in the conversion of primal into the corresponding dual, okay. So let me insert table. So let me make it as it is. So primal, and here dual. Okay, so the first point, is primal if it is a maximization, that this dual is going to be the minimization. Okay. Second, if primal contains n number of variables and a small m number of constraints, then dual will have a small m number of variables and small n number of constraints.